Good morning, everyone. This is a morning. I should hear loud from you guys. Good morning, everyone. That's great. So, distinguished delegates, guests, and colleagues, as we enter the third day of India Energy Week, here we will delve into an important and relevant topic of the day, which is hydrogen. We have already embarked on the journey of Viksit Bharat, which talks about growth, which talks about energy growth. And here, hydrogen becomes a transition fuel which will help us in bridging the gap of sustainable energy as well as meeting the energy demands for the country, which is growing. The National Green Hydrogen Mission, which was launched, also is the step to achieve this growth, with an initial outlay of 19,744 crores for development of the complete hydrogen ecosystem across the country. And this will help us as a country become a global champion in green hydrogen. With this, I will not be standing in front of you, and I would like to start with the speakers so that they can come and present their views about the various things which they are doing in their industries, which is helping us in production, development, and end use of hydrogen. So I would like to invite our first speaker of the day, Dr. Surjit, who is from DGH, to come and share his views. Dr. Surjit has over 16 years of experience in oil and gas sector. He has a portfolio of more than 20 international publications, and his expertise spans from structural framework, interpretation, seismic factors, attribute analysis, reservoir modeling, and risk analysis. So please welcome Dr. Surjit as the first speaker.
Thanks, Ankur, for the lovely introduction. Anyway, before going to the integrity of this topic, let me introduce again myself. I am Surjit Gorai, a geophysicist in profession, having more than 17 years of working experience in oil and gas industry. Since last 5 years, I am associated with Ministry of Petroleum Natural Gas, and I have the opportunity to work with all the GNG related data in all Indian sedimentary basins. And this motivates me to relook and reassess the data in order to find out new areas of exploration. Keeping this view in mind, I have tried to study a number of projects, and I am excited here to present my recent work on exploring white hydrogen potential in Andaman Nicobar Basin. Now, before going into the integral part of white hydrogen, it's my duty to introduce to the audience the backgrounds. So, I will discuss why and what part first. Now, before white hydrogen, we should know about hydrogen energy. As per the definition, hydrogen energy is a form of renewable energy that involves hydrogen as a fuel. It can be produced from various resources and used in different applications to generate electricity from hydrogen. Based on the methods to produce hydrogen and environmental impact, hydrogen energy has been classified in different forms based on its color, like green, blue, gray, yellow, aqua, brown, gray, black, and finally the white hydrogen. Now, the definition of white hydrogen is, this is the naturally occurring hydrogen which is trapped under the subsurface, and this is the pure form of hydrogen. Now, question arises, why white hydrogen is becoming so important nowadays? This is because it provides a sustainable energy solution, it is abundant in nature, it also provides the global transition to the white hydrogen economy, as well as it was a potentially abundance in nature. Now, next question arises, how it's formed. If you go through the genesis of white hydrogen, it is basically formed from the Earth's core. It is released from the Earth's core directly and trapped in the sedimentary basins through the serpentinization process. Basically, serpentinization is the water reaction with iron-rich minerals which produce natural hydrogen. And it is also produced from some reducing agents from mantle, some radioactive elements, and decomposition of organic material. Now, how it is occurs in nature? It occurs in various forms, like in free gas form, basically in oil and gas field, in ore bodies, kimberlite pipes, volcanic gas, hot springs, and fault networks. In absorbed form, it is available in sedimentary basins. In inclusion, it is in ultrabasic and precambrian and igneous rocks, and dissolved in waters, basically in hydrocarbon fields, groundwaters, and the old precambrian rocks. Now, to understand this white hydrogen more deeply, recently researchers has classified and developed a model called hydrogen system model. It talks about this dynamic behavior of white hydrogen in geological environments. It also talks about its generation, migration, entrapments, as well as the production technology. Now, if you go through the exploration history of the white hydrogen, there is a funny story there. During 2018, this white hydrogen was discovered by accidentally in Mali, and since then, it attracts the attention of peoples, and recently an extensive work is carried out in Africa, Australia, Europe, and USA. Now, coming to the basic main integral part of this discussion, that okay, this is the background of the white hydrogen, and it is important nowadays. Is there any possibility in India also the similar setup is possible? Now, I have tried to use these recently acquired data by Government of India. This data is from Andaman Nicobar Basin, and this is the spreading center, and this line is from this in the spreading center only. A number of lines is there, and this specifically this east seismic profile attracts my attention, and this amplitudes is very interesting. Now, after integration and interpretation aspects, I have found a conceptual hydrosystem model. This is maybe the main spreading centers, and this is the fault networks. Now, the presence of spreading centers provides that iron-rich minerals like olivine, pyroxene, and these fault networks provide the inclusion of fresh water with iron-rich minerals, and which helps in serpentinization process to produce hydrogen. Now, if you see that the top layer, this is the marine cell, which very effectively can trap this hydrogen generated through this serpentinization process, and this amplitude may be that due to this hydrogen. Now, I have done some more advanced study. This is that RMS attributes map of the same profile. Again, in RMS also, this amplitude is stand out, and similar concept I have adopted here. And this is the same model which again justifies that conceptualization of serpentinization and the accumulation of hydrogen in these amplitudes. this is the zoom version of this. This is, and just to show that faults also helps in trapping this hydrogen. And this fault helps in inclusion of fresh water with that surrounded iron-rich minerals and which produce hydrogen. Now this is the whole collage just to show that there is a system may be available there to generate white hydrogen. Now our job is to target these areas with respect to exploration points. Till now no exploration activity has been done with respect to hydrogen, though people have talked about some other gas presence there. Just to confirm that conceptualization, I have considered one section more. This is the north-south section. Again, this is the conceptualization that this is the this is the spreading center which provides the requisite heat and temperature and the iron-rich minerals, and these faults provides that inclusion of fresh water into these rocks, which helps in serpentinization and produce hydrogen, and it may be accumulated there. Again, this is the RMS distribution, just to show that the anomaly is there. And the same thing, this is a cut in the same RMS distribution. And now, just to show that how hydrogen can be trapped there in this fault network and this extension. Now this is the collage of that north-south section. Now again, recently in 2024, Dodson has again proposed a conceptual hydrogen accumulation place. And in GeoExpo, he has hypothesized that near the spreading, near the subduction, there may be a possibility of trapping of white hydrogen. Now, the similar setup existed in our Andaman Basin also. This is the section, and this is the cartoon I have drawn there, and these are the locations where white hydrogen can be trapped there. Now, in summary, I can say that there is a good future in India for accumulation and exploration of white hydrogen, and Andaman Basin can provide the key prospect area for this clean energy, which can be cost effective, which supports the energy transition and also aligned to the net zero target of the government of India. And most important thing, it is once it is founded, it is abundant in nature. So, and as a byproduct, it can produce that fresh water. So there is a good potential and future of white hydrogen in India. And this is my submission. If anyone have any doubts, he or she can come to DJ stall. There is some discussion elements there, so you can come and discuss with us. Now finally, I extend my sincere gratitude to our DG ma'am and ADG sir, as well as HOD, to provide me the valuable guidance and encouragement for this study. And that's all from my side today. Thank you.
Thank you, Dr. Surajit, for your thoughts about white hydrogen and a possibility that India can have white hydrogen inside, which will help us in decreasing the imports bill which we get for the energy demands. Now with this, I would like to invite our next speaker, who is Mr. Subodh from Oil India Limited, and he will be talking about his studies done for effect of hydrogen in domestic gas burners. Mr. Subodh is a chemical engineer with more than 20 years of experience. He is involved in various research in oil field chemicals, flow assurance, well simulations, and green hydrogen, to name a few. A huge big round of applause for Mr. Subji.
Good morning, everyone. And first of all, thank you, Mr. Ankur, for such a generous introduction. I'm Subodh, and I'll be presenting our work that we did as part of our collaborative approach with some institutes, and more so, what we did in our fields there in Duliajan. My work here would be, what I'm going to discuss here would be color agnostic. We heard Dr. Gorai talking about different colors of hydrogen and how tremendous seismic work he has carried out in the Andaman Basin to locate the source of the next generation source for energy. Uh, for me, as I said, the work would be color agnostic. Whatever we do, eventually we need to use the hydrogen from wherever source we are going to use it, whether it is gray, green, yellow, golden, or for that matter, Dr. Gorai's white hydrogen. Now, when we end up with hydrogen, a lot of hydrogen, and then we've been talking about how to use hydrogen, but as a common man's point of view, we need to understand what are the basic things that we need to do to make our economy amenable towards utilizing hydrogen. So let's start with the domestic PNG network, so to say. There is a mandate by PNGRB to start blending hydrogen into natural gas pipelines and to utilize into the domestic network. So here in this particular case study that I'm going to discuss about in the next couple of slides, I would be showcasing the work that we did here as part of our study in our field headquarters. So the objective, as I mentioned, was to just to assess what would be the burner performance of the typical burners that we use in our domestic setup there in our housing area, in order to understand the flame characteristic, the temperature, behavior, and the similar aspects. So this study was undertaken by the Indian Standard Guidelines listed out there, IS 14612, and then the power ratings of the burner ranged from 1.2, 1.3 to 1.63 kilowatts. And the flow rate that we maintained was roughly around the flow rate that we see in the domestic PNG network of 3 LPM. So as you could see here, the test matrix actually composed of, we varied from the 0% hydrogen, the natural gas, the base case, and then we started off from the 0% hydrogen in methane way up to, in 10% increments, way up to 30% blending. So as you could see here in the test matrix there, when we do not add any hydrogen, for the sake of uniformity of our experimentation, we substituted the natural gas that we produce with a more uniform and high purity grade methane, because the methane, that natural gas that we produce, contains roughly about 98 to 99% methane in our fields. So for the sake of experimentation and ease of doing the experimentations, at the design stage, we started using methane as a surrogate fuel for natural gas. So if you could see the table test matrix there, with 0% hydrogen, the calorific value stands around 50,000 or so kilojoules per kg. And with the blending in 10% incremental, the calorific value did increase to about 53. However, the increase is not so into the volumetric density, if you could see, because we are diluting it with a lighter gas, and therefore the mixture densities started gradually declining as we kept on increasing the volume percent of hydrogen into the methane or the natural gas component. And this actually is also indicative of the fact that the power rating of the burner also started decreasing from 1.63 to 1.29. This is not the typical LPG burner that you may have come across. This is the burner that we use here, there in our oil fields, way in our Duliajan field headquarters. And this is a very typical burner. It has been working there, and we started long back. Even the concept of PNG started in India, because we, being the producer of natural gas, we started using the lean gas, which had at that point of time could not be economically monetized. So that was fed into our own network so that it could be used for heating and cooking purposes. So this is a typical burner that we have there. And if you could see here, it's a ring-shaped burner with 28 holes there onto the burner body. And there's an entrainment hole about 10 to 11 millimeter, which actually entrains the air, which ensures the adequate fuel mixture when the fuel is being fed into the burner. And the right side picture that you can see actually is how the flame is anchored into the burner at the studied flow rates. And the burner had a 1.6 millimeter dia in the injector port, which ensured adequate mixing and dispersion of the fuel into the burner. Yes. So this is what our experimental setup consisted of. We used an aluminum pan of about 9.4 kilogram, and we ensured that the uniformity was all across there while we tested and carried out the thermal behavior of the burner that we studied. And there were enough instrumentations were in place to measure the temperatures of the vessel, of the flame, as well as the burner top or the metal part of the burner, so as to understand if at all we need to get into the transition mode of utilizing the hydrogen that we produce there, or any hydrogen source that we would be blending, our burner, whether it's going to withstand the temperatures, our burner, whether it's going to withstand the metallurgy, would withstand the temperature profiles and so on. So that was the entire purpose to detail out the entire instrumentation that we did. So this is the actual setup. The previous one was the schematic. So this is what the entire experimental setup looks like. We had a couple of array of thermocouples all across our burner body, as well as the water temperature was measured inside the aluminum vessel. And then we had this adequate data acquisition system, which ensured that the repeatability was ensured all throughout the experimentation. This was the methodology. This is all the engineering science that we study way back in our BTech levels. So this is what we did, and this was the methodology that we adopted for calculating the efficiency of the burners. Now the results, if you could come across, we've been talking about, yes, hydrogen, hydrogen, and hydrogen, but actually when we start blending it, we would see that, yes, it is a very high calorific value, but it would only add value in terms of what we are adding on to. Let's say the general perception is if we are adding hydrogen, is going to increase the calorific value. But we need to be very, very clear with regards to the unit that we are talking about. If we are actually adding hydrogen by volume, then we are going to dilute the gas, and therefore there would be reduction of the volumetric calorific value, so to say. But on a per kg or per mass basis, we would see some significant improvement in terms of the calorific value. Nonetheless, if we try to assess any burner through those standards out there, we need to ascertain and then do a moving average of the temperature profile, so as to understand at what temperatures that it's going to equilibrate out. So the final water temperatures, if you could see in the experimentation, it equilibrates out to about 80 to 90 degrees. So throughout the entire experimentation, this is with a 0% hydrogen, the burner on pure methane fuel. So at around 80 to 90 degrees centigrade, the thermal efficiency is leveled out around to 66.2%, if you could read the graph there. Now with the addition of these hydrogens into the natural gas stream or the methane that we use for our experimental purpose, as we kept on increasing the percentage in the hydrogen from 10, 20, 30%, you can see that amount of heat, the duration that we needed to provide the heat energy actually increased from 32 seconds with a 0% hydrogen into the methane, and it increased way up to 45 seconds when we started blending at 30% by volume of hydrogen. And this is the reason why we primarily saw the decrease in the power ratings of the burner. So this essentially means for a household, if you are blending it for the sake of blending hydrogen into natural gas stream, we would be probably ending up with a increased amount of cooking time. Here it is roughly about 15 seconds from no hydrogen to 30% hydrogen. But again, this is very specific to the burner that was studied and taken for experimentation purpose. And again, as I said, the power rating, if you could read the chart there, with no % hydrogen, the power rating was something around, thermal efficiency of the burner was around 66.2%. And then with spikes of hydrogen, it increased up to 10. When we added 10% hydrogen, we could see it increased about 1% point, and it was there around 67, 68% thermal efficiency. However, with continuous blending of hydrogen, we noticed the thermal efficiency going down, more so because if you could see this graph, because we were heating the entire vessel, the aluminum vessel, for the same amount of time for zero case, Vis-a-vis for the 30% blend, we were taking more time, and therefore there were more heat loss, which resulted in decreased thermal efficiency of 30% blend. So with 30% blend, the thermal efficiency what we found was about 64% at max. But to talk about the flame characteristic, now there is a lot of doubt which goes on in our minds that whether addition of hydrogen would bring in any additional challenge in terms of the flame stability, flame anchoring, and so on. But if you could see the pictures there, we did number of visualization studies and we captured everything. The flame did anchor very well from 3 LPM to up to about 25 LPM at such high rates also. The flame could easily be anchored onto the burner ports, the nozzle of the burners. And then we did a calibrated approach, and after multiple analysis of the images that we generated, we came across that to the conclusion that the flame geometry was of conical shape. And as we kept on adding hydrogen, the flame cone actually started reducing. So if you could see from with 0% hydrogen in the blend, the flame cone radius was about 4 mm, which got reduced to about 3.6. However, the equilibrium flame temperature added kept on increasing as we kept on increasing the blend of the volume percentage of hydrogen into the natural gas. This is because hydrogen being very reactive, it actually burns efficiently, and therefore the equilibrium flame temperatures were, from a no-case basis to a 30% blend, we saw a marginal increase in the temperature, and so is the case with the laminar flame velocity. This figure shows the flame temperature versus hydrogen addition into the methane stream. If you could see, the flame temperatures actually did increase marginally in the range of about 5 to 15 degrees centigrade for different blends that we came across. This is primarily because as the mole fraction was added more, there was more amount of hydrogen being readily available, and therefore this increased the flame temperature. Similarly, the burner wall temperature with addition of hydrogen we carried out and we assessed. There was not very significant increase in the burner temperatures. The base case with 0% hydrogen was 136 degrees, and it increased up to a rough and leveled around at 140 degrees. So about roughly 10 degrees centigrade was the increase or hike in the temperature across the burner body. So this essentially led us to the conclusion that we would not require any significant changes in the burner that we have there in our facility. So to conclude the summary, as hydrogen percentage keeps on increasing, the mixture calorific value would increase. However, the mixture volumetric density would decrease. And at constant volumetric flow rate, the one that we studied of 3 liters per minute, the power rating of the study burner decreases as the mole fraction of the hydrogen kept on increasing. Again, this kind of studies are very highly burner specific, and then for us, the case was to see and evaluate whether the burners that we have in place, whether we can readily deploy and utilize it without changing anything. And yes, this study shows that we can actually safely keep on utilizing the burner for our end users application that we have. And the last point, we did extensive experiments with hydrogen blended fuel up to 13%. We have had nil incidents of any flashback or the burner instability issues that we came across. So the entire experimentation was very safe up to 30% whatsoever, and we never saw any flashbacks or any issues with the flame stability. So that's all from my side. These are some of the references there. If you would like, you can refer to those references. And thank you all for your patient hearing. Thank you.
Thank you, Mr. Subodh, for your thoughts and sharing real case studies. Now with this, we will now move ahead and we'd like to invite our third speaker of the day, Mr. Vijay from EIL. He will take us through a little deeper and will share his experience on development of indigenous deoxyreactor technology for hydrogen purification. Mr. Vijay is a seasoned professional having more than 18 years of experience in R&D field. He was involved in various developments such as coal gasification, coal methanol conversion, crude oil desalting. So let's welcome Mr. Vijay on stage.
Good morning to all the esteemed audience and the IEW for giving us the opportunity to present our case. So broader aspects for green hydrogen with respect to the technology, policy and infrastructure are being discussed very extensively among the industry experts, stakeholders and policy makers. So here I would be talking specifically hydrogen purification, which is an incremental value proposition as part of EAL services and capabilities. So that presentation outline, I will touch upon what is the current hydrogen demand globally and with respect to India and its value chain and EAL's involvement in the value chain over the years, and green hydrogen, what is the definition, and the electrolyzers which are prevalent in the industry, and the green hydrogen purification technologies which are there in the literature or otherwise, and EAL's experience, what we have been doing in this area for a couple of years now as a diversified portfolio, and the deoxo reactor technology which we have been working in our R&D center, Gurugram, and finally summarizing the discussion. Yeah. Presently, world's hydrogen demand as per 2023, this is international reports suggests that 97 TPA. In that, around 9% is India's consumption, and it is proposed by 2030 it would reach around 150 million metric tons of hydrogen per annum. And if you look at the consumption in different sectors, mainly refinery, the bottom portion, bottom portion is refinery and the balance is industry. So since 2019, if you look at, there is no other areas hydrogen consumption, whereas it is projected by 2030, various industries like power, synthesis fuels, transportation and other industry will also contribute a lot as far as hydrogen consumption is concerned. And in that, by conventional means, maybe steam reforming and other means in the which are there in the refinery, and balance is proposed to come from the renewable sources. So as far as India's refining sector is concerned, present production is around 256 million metric tons, and the hydrogen consumption is around 2.5 MMTPA, and it is projected by 2028 it will be around 310 MMTPA, and the consumption would be in the range of approximately 3 MMTPA. So there is a tremendous potential for absorption of green hydrogen, and if you look at the fertilizer sector, similar phenomena prevails. There also substantial hydrogen consumption is there, so that is also an avenue for absorbing the green hydrogen. Yes, hydrogen value chain. So EAL as a company has been involved starting from input handling the feed sources, and also the production, distribution and application. Feed sources meaning handling NG, naphtha, whatever the required feed for producing the hydrogen, and presently involved in the green hydrogen projects as well. So looking into water and renewable power, etc. And production, we have been there and providing various services as part of that conventional steam methane reforming, and adding to that we are carrying out some feasibility studies for carbon capture and sequestration, and intermittently whatever is produced hydrogen in the different units, it may be CCR, CRU, hydrocracker, etc., and electrolysis, and we are there in the distribution also. We are working on various projects for transportation and storage already there, so other means of transport and liquefaction. And applications, as I mentioned, that we are there in refinery, ammonia, fertilizers, chemicals, and buildings and power we are working on with various stakeholders. So therefore, EIL is committed to contribute and provide the support for the customers across the industry. So as far as green hydrogen, everybody may be aware of that the Ministry of New and Renewable Energy has recently notified that non-biogenic GHG emissions less than 2 kg of CO2 equivalent emissions is considered over for 1 year average. It is considered as green hydrogen. So the means can be either it can be electrolyzers or through bio route. It may be biomass gasification or biopyrolysis and subsequently bio oil conversion to green hydrogen. So it is a very sustainable and fuel. It has got a very high energy density and it can be stored as well, and it can address the very hard to abate sectors as well, and a reliable source of energy. So National Hydrogen Mission, this is also more or less most of the people may be knowing that it is a very incentivized mission has been announced, wherein R&D has been given thrust in that to develop indigenously various solutions for this green hydrogen technologies. So with a target of 6 lakhs jobs, 60 to 100 gigawatt equivalent electrolyzers, and it has a mission to produce renewable power, 125 gigawatt of renewable power, and with a target of reducing the 50 million metric tons of CO2 equivalent, and the investment is in the range of let's say 8 lakh crore is targeted by 2030, and the total production target is 5 million metric tons of green hydrogen by 2030. Yes, we have been working in the industry for technology selection for various clients we are working with, whatever the prevalent electrolyzers technologies are there. So just I tried to capture few points out of this. This alkaline based and PEM based technologies are prevalent as of now. Others solid oxide electrolyzers are in the nascent stage. So if you compare a few important aspects of this, electrolyzer, it is a very well established technology over the years, and the stack sizes are a little bit, you get a maximum stack sizes maybe 5.5 megawatt stack sizes, but it has a little startup time, it takes a little longer compared to the this PEM electrolyzer, and it can produce up to 30 bar hydrogen, and the produced hydrogen will have little oxygen. So that need to be addressed. And coming to the PEM electrolyzer, it is gaining the momentum in the industry, and the stack sizes are little lower compared to this, but it is more robust in terms of startup. It can start very fast compared to the alkaline electrolyzer. So where the very dynamic requirement is there, in that case PEM electrolyzers would be suitable. So depending on the application, EAL can suggest the suitable requirements for the industry. And so purification routes, as far as gas purification is concerned, many routes are there, starting from cryogenic, membrane based, pressure swing adsorption, and ultimately catalytic route. That cryogenic is very energy intensive, and pressure swing adsorption, there will be a substantial loss of the produced hydrogen. And meeting that stringent requirement of oxygen less than 5 ppm in the downstream, it may be in the refinery application or other fuel cell applications. But catalytic recombination is found to be most effective, and more or less no loss of hydrogen whatever is produced by supplying a lot of energy in the form of power. So membrane separation, pardon. Yes, membrane separation, polymer membranes may not be able to give the desired purity, whereas metallic membranes are there, they are in the nascent stage, but it is very costly as of now. So this EAL's experience, starting from electrolyzers, as I mentioned, that we are working for various clients as per their requirements, PMC services, selection of LEPC contractor for supplying the electrolyzers, etc. And the balance of plant design, we are working on few inquiries. And infrastructure, the transportation infrastructure also we are working on, and various derivatives, green ammonia, and other allied derivatives of green hydrogen. We are working on various feasibility studies and other projects in the industry. So these specific details, our technology, other technical people are present in the conference. You can visit our stall so that if you have any requirement, we can discuss. So coming to the deoxo reactor technology, the oxygen produced from electrolyzer will have 0.2 to 0.6%. Hydrogen produced from electrolyzer will have 0.2 to 0.6% oxygen. So if you gets into the downstream, unnecessarily it will induce side reactions, or it gets accumulated in the gas loops, or otherwise it will create corrosion, etc. Those aspects are there. So it is a highly exothermic reaction. One has to handle with carefully in terms of distribution in the reactor and other aspects of the process. So this is a very critical item in the downstream of the electrolyzer. Presently, it is provided as a package item. You have to take it from them only. There won't be much flexibility for the client. And generally, platinum or palladium based, precious metal based catalysts are used to purify this oxygen, to purify this hydrogen. But if you just go through the literature, you will find that mostly it has been applied for oxygen rich and hydrogen lean streams in nuclear applications, etc. So we found that there is a potential and value addition in the downstream of the electrolyzer. As a balance of plant, we can add the value. So, and moreover, we have been designing the reactors over the years, and we have a very robust design capabilities as far as these reactor designs are concerned. And optimization scope exists down X electrolyzer. There is a scope which can be integrated with the existing assets of the clients. So we have a state-of-the-art testing facilities in our R&D center. So the left side one is the facility which we have, where we can put the catalyst up to, let's say, 200 grams of catalyst. So we have identified the catalyst, various catalysts, and carried out the experiments. And this is how the reactor configuration. It is a reactor with 100 cc catalyst can be put. Top, we are putting like actual reactor in the plant. So initially inert material will be there. After that, catalyst will be there, and downstream of that, again inert material, so that the hydrodynamic profile is maintained. The same profile is being put in our reactor in the R&D center, and we are working on it. And we have tested up to three, as a gas, feed gas, we are taking hydrogen, nitrogen and oxygen, as we cannot take the mixture of hydrogen and oxygen in the same cylinders. So we have tested up to 0.2 to 3.5%. In case of any slippage also, it can address. Operating pressure 5 to 30 bar we could conduct the experiment. And temperature, it is a reaction which occurs at ambient temperatures. And the quantity we can take 50 gram catalyst, since it is a very highly exothermic reaction, and we are handling with very trace oxygen. So we cannot, to determine the actual concentration in the product, we need to put little lower catalyst in the reactor. So during the study, we found that the reaction is very fast and follows zero order, or in between 0 to 1 the reaction order, and we are able to meet the target specification of oxygen 0 to 5 ppm in the treated hydrogen. So in summary, what I could say is that we have the expertise in offering the deoxo reactor design as a balance of plant, which is a complementary strength of our core strength of our organization. And the in-house know-how, substantial know-how we have, so that is being extended to design this reactor. Yes, and scale up can be done no need of any other scale-up studies because we have already carried out for various applications over the years. So all the hardware required, we have that proprietary hardware with us, and it is a cutting-edge solution which can be implemented in the balance of plant. This indigenous solution can be absorbed, and it will have more flexibility where it can be integrated with the existing assets. So by this method, it can add value and reduce the cost of the overall electrolyzer and the plant. So with this, thanks, and thanks for your patience. Thank you, sir.
Thank you, Mr. Vijay, for your thoughts and bringing out the value proposition that this deoxy reactor brings for the balance of the plants. Now we move ahead for our next speaker, which is Dr. Bharti from HPCL. So, she will be talking about the in-house design of green hydrogen production technology with reduced capex. Dr. Bharti is a senior research scientist having more than 15 years of experience in renewable energy and green hydrogen. She has been the recipient of several awards, including the Top 50 Women Achiever Award in Science, Technology, Engineering and Mathematics by CII. So let's welcome Dr. Bharti on the stage.
Thank you, moderator, for a nice introduction. Good morning, everyone. So my previous speakers actually set the tone for my presentation. Thank you. Thanks a lot. So today I will be speaking about in-house design green hydrogen production technology with reduced capex and opex, development and demonstration. These are my team members, and I am from HPCL R&D Center. So this is how my presentation I'll be talking about. As my previous speakers already discussed about the global hydrogen demand and the role of the electrolyzer, maybe I'll be skipping that. And what is the R&D's approach towards the green hydrogen production? What is our anion exchange membrane electrolyzer technology? How we have reduced the capex and the opex with implementation of our technology? And currently we have demonstrated 1 megawatt equivalent electrolyzer by adopting the anion exchange membrane technology, which is in very nascent stage worldwide, and the conclusion and takeaway. So I'll be just keeping these things as my previous speaker already explained. In this figure, I would just like to emphasize, like China is consuming 28 million metric ton of hydrogen, like in 2023. And next is the USA, which consume less than half of the hydrogen consumption done by China. But if we, being a refiner, when we are touching about the consumption of hydrogen in the refinery, there is a prediction that the hydrogen consumption by 2023, it will be reducing to 35 million metric ton because of the implementation of various renewable energy in the mobility or the transportation and in the other sectors. And if we discuss about the like the hydrogen production that can go by is 2030, what are the different countries' contribution will be. So here we can see that the Europe and Australia, they are in the top, like in the electrolysis or the fossil with CCUS. And these are the different technology that has been implemented. So here we can see that alkaline is basically capturing the market with more than 60%, followed by the PEM, which is currently in 22%. And if we see what are the different countries that they are announcing the project. So as I mentioned in my previous slide, China is consuming more hydrogen globally, but if we see here, the number of announced project, or even if we are discussing about the projects that cross the FID, the final investment decision, the China is top. So,
good morning, ladies and gentlemen. We welcome you to third edition of IEW 2025. The show timings for today are from 10 a.m. to 6 p.m. All the visitors, exhibitors, and delegates are required to wear their badges at all times. Children below 18 years will not be allowed inside the hall. Please take care of your belongings. Thank you.
Sorry for the interruption. So if you see like the FID, the projects that has been passed, it is only 4%, but whereas the prediction is pretty higher. So this is one concern that when we are discussing the implementation of the green hydrogen uses in the refinery or the industries. But one good thing is when we compare like 2022 or 2023, like what is the percentage of the electrolyzer installed capacity has been increased? It is 9x, which is pretty good. And if we see the electrolyzer manufacturing capacity, that has been increased like from the 2021, it is in the 4 times. So though the few projects are crossing the FID stage, though the announced projects are pretty higher, as there is a prediction that by 2023 the announced project related to the green hydrogen will cross 520 gigawatt. But if you see the FID stage, it is only 230. But still there is an increase in the electrolyzer installed capacity along with the manufacturing capacity. So this is a good thing for the like towards the net zero, achieving towards net zero. So while discussing what are the different type of electrolyzers technology that exist, so this is the alkaline or the anion exchange membrane. The working principles are pretty similar, but there is a difference in the severity or the different components that we use in a electrolyzer stack or the BOP. So here basically the hydroxyl ions that passes through the cathode and anode. So this is how, and the hydrogen produced in the cathode side and oxygen produced in the anode side. This is the PEM electrolyzer. So here basically the H plus ion that transport throughout the membrane. And then another technology is the SOEC, that is the solid oxide electrolyzer cell. So here basically the O2 minus that transport through the membrane, and these are the solid membrane, the organic based membrane that people used in this SOEC technology. So here I'll be discussing the anion exchange membrane electrolyzer technology that we have developed. So what is the HPCL R&D's approach while starting the project? So here our main approach is how we can develop a cost effective and efficient catalyst that can basically increases the efficiency and that can reduces the ohmic losses by better conductivity. How we can go to transition metal fully, and how we can increase the current density by controlling the state of the art material design, and how we can reduce the material loading, like how much amount the mass of the material that has been loaded per centimeter square of the electrode size. And with that we can decrease the cost of the electrode. Then coming to the operational severity, as alkaline basically operate more than 38% of the KOH. So here our main aim is how we can reduce the percentage of the KOH in the electrolyte, so that we will have a less corrosive environment, which will be better for the environment, along with the different component of the electrolyzer stack, because with corrosive environment, the life of the stack will go down and the maintenance cost will of course increase. How we can operate the electrolyzer at low operational temperature, less than probably 60 degrees centigrade. So these factors will enhance the durability of the stack. And coming to the stack design, when we are designing the end plate or the bipolar plate, or if we are discussing like as a whole assembly, how we can make our design more compact so that there will be a zero gap. It will form a zero gap electrolyzer stack or a single cell we can say, and that will basically reduces the ohmic losses, and it will there will be a reduction in the resistance, and that will lead to the high current density. And another thing is how we can enhance the hydrogen purity directly from the stack. As my previous speaker discussed about the deoxo unit that we basically use this in the downstream to get the better purity like 99.9 plus. So how we can directly get the high purity hydrogen directly from the stack, whereas we can skip the deoxo unit, which basically uses very like the precious metal like platinum and palladium, which my previous speaker explained really well. So this is the demonstration that we have done in our R&D of 10 kilowatt electrolyzer. So the right hand side shows the technical specification. Like here we can see we are using the KO is less than 5 watt%, the temperature is around 50 degrees centigrade we operate, and the power consumption is only 49.5% per kilowatt of per kg of hydrogen production. And here you can see the purity that we achieved is 99.9 to 99.96%. And we have demonstrated both in the lab and pilot scale, and we have filed 6 patents across the world. Then how our journey is, like in November 23, we have tested a 1 kilowatt stack of 100 centimeter square active area, electrode active area. Then we have scaled up to 500 centimeter square active area in June 2024. So this is the 10 kilowatt hour stack. And for this stack development, we have received the Best Innovation Award from MOCNG from the CST during the Energy Technology Meet November 2024 for our anion exchange membrane technology. And in February 2025, we have developed to 1 megawatt equivalent stack, which we have tested of 25 centimeter square. So here this is how this is the electrode, the structure, so which we have fabricated. So this is basically a bifunctional electrode. The same electrocatalyst can be, or the electrode can be used for anode and cathode. So that will reduce the fabrication cost. Then this is the electrode that we have scaled up to 1 meter diameter, which is really challenging in case of the anion exchange membrane, or with an approach like how we can reduce the mass loading, how we can skip the leaching of the material when we are operating when we are producing high quantity of hydrogen with low power consumption. So this is how we have scaled up to 1 meter square. This is the end plate, and this is the stack that we have tested for 25 kilowatt hour. So here, this is a 3-cell stack. So to make it 1 megawatt equivalent, we are planning to make the size of the electrode same. We will be just adding off another 120 odd number of cells in the stack to make it 1 megawatt. So this is India's first in-house designed large-scale electrolyzer technology that we have developed and demonstrated. So the working principle, like here we have used transition metal. So this is a ferrite-based structure. So here basically the 3D orbital of the transition metal and the oxygen 2B orbital, that is a overlapping. So how we can control the electron density, how the overlapping will be more efficient, how the electron density can be enhanced, and how the transport of the electron can be happened with low resistance. So these are the different approaches that has led to make a efficient electrocatalyst. So here we control the oxygen vacancy that will lead to the and the electron density in the 3D orbital or the overall system. So that leads to a better efficient OER and the HER half cell reaction that basically leads to the oxygen and hydrogen production respectively. This is the testing that we have done at 1.9 volts. So we have tested for almost 4 to 5 months to see the stability, which is pretty stable. The enhancement in or the over potential that basically increases is in 0.0 odd microvolt, which is acceptable with respect to the commercial electrolyzers. So when we compare our technology with respect to the existing technology, so here we can see that the power consumption wise it is very less with a better efficiency close to 80%, and we are using at low severity condition. Same bifunctional catalyst can be used for both anode and cathode. So this is basically a viable technology competitive with the commercial electrolyzers that is there in the market. So coming to the novelty, like the stack design that we have done, the controlled operational parameter where we are getting a better purity of the gases. The design of the electrode that basically act as a gas diffusion layer and the catalyst layer, the development of the efficient and cost-effective catalyst, then which reduces basically the processing cost. In the downstream, we don't have the deoxo unit as we are getting the high purity from the stack. And another important thing is we can operate at the minimum of 10% load. So that will enable the easy and low resistance integration to the seamless integration to the renewable systems. Then how the capex and opex has been reduced. So this is the data I have taken from the IEW arena, the reliable sources. So basically, in a system, the stack contribute 50% of the total cost along with the other component. Coming to the stack, the electrode basically contribute to the 48% of the total cost, membrane is 37, and the bipolar end plate gaskets are 15%. So here what we have done by our innovative approach and the state-of-the-art technologies, we have reduced the catalyst cost to 80% and the membrane cost to 60%, which basically contribute to the 44 and 26% to the stack cost. And when we are talking about the OPEX, as the power consumption is less, 12%, and as we don't have the deoxo unit, which contribute to the 2% of the total power consumption. So in the CAPEX, we have reduced the 35% of the total system, and in the OPEX, we have reduced 14% of the total system. So this is how the CAPEX and OPEX reduction that we achieved. So this is the technology highlight, like 1 megawatt equivalent stack we have developed with reduced CAPEX and OPEX with low severity operational condition and low footprint. It is a modular design. We can install in whenever there is a requirement of the hydrogen. So the way forward is like, as we already achieved 1 megawatt equivalent stack, so now we will be demonstrating the 1 megawatt anion exchange membrane, and also the AEM, we have alkaline technology too. So the demo plant of 1 megawatt will be demonstrating. So the key takeaway is like HPCL has designed and demonstrated the efficient, cost-effective 1 megawatt equivalent electrolyzer stack for both AEM and alkaline. We have reduced the CAPEX and OPEX substantially, which makes it more easily adaptable for the industry for the green hydrogen net zero approach. And we offer, along with this technology, other electrolyzer technology that can implement the green path energy that we can adopt easily. Thank you for your time.
Thanks, Dr. Bharti, for sharing your thoughts on how the CAPEX and OPEX can be optimized. And we all know and will agree, cost plays a very vital role in making any technology developed and adopting as soon as possible. With this, where we talked about the cost reduction, now we will touch upon another topic about the efficiency of the electrolyzers, and would like to call upon multi-skilled personnel from BPCL, Mr. Herschel. Why I called him multi-skilled? Because apart from being an engineering professional, he has also completed postgraduate diploma in business and corporate law. He has a PG diploma in renewable energy management, and he also takes care for cyber security. So please welcome Mr. Harshit on stage.
Good morning, all of you. I am Harshal Talele from Bharat Petroleum Corporation Limited. My topic is the optimizing electrolyzer efficiency through the strategic integration of magnetic field. Before dive into topic directly, I will go through what is the importance of hydrogen. And it is very difficult to give the last session because most of my slides is already covered by the other speakers. I will go through it. As you know, our India's primary energy consumer is the third largest energy consumer in India, but it is also a third largest emitter of carbon dioxide. Therefore, there is a must need of renewable energy in India, and recently we crossed the 200 gigawatt mark in 2024, and the main contribution is through the solar power, that is 91 gigawatt, and wind power 50 gigawatt. In last 10 years, we saw the almost 8 times increase in the renewable energy, and we are the fourth largest RE producer in the world, fourth in power and fifth in solar. Also, India present a 5 nectar element, that is Panchamrut, recently in COP26, and these are the 500 gigawatt non-fossil energy capacity, the 50% of energy consumption through the RE, the reduction of carbon emission by 1 billion tons, and net zero by 2070. One more important target is taken, that is energy independence by the 2047. But to achieve this, solar and wind is not capable. That's why hydrogen is the major contributor for achieving this goal. And therefore, in 2023, the National Green Hydrogen Mission is launched. And as per that, the 5 MMT green hydrogen per year is to be generated, and manufacturing of 6 to 100 gigawatt electrolyzer capacity. For that, 125 gigawatt RE, dedicated RE is to be installed. As you know, the hydrogen is an energy carrier, and if you produce the hydrogen through the RE, it is called as green hydrogen. And what is the importance of hydrogen? Because hydrogen is the first element in the periodic table that all of you know, but it is colorless, odorless, tasteless, non-corrosive, non-toxic. That's why it is a perfect fuel for the future. But problem is that if you see the composition here, there is a negligible amount of hydrogen available. Therefore, we are producing hydrogen from the fossil fuel, that is natural gas, oil and coal. But in that problem is almost 10 to 19 kg of CO2 is emitted for the production of 1 kg of hydrogen. But hydrogen specific energy is 3 times higher than our gasoline and diesel, almost 30 to 90 times higher than our battery. As already talked about the different colors of hydrogen, I will skip this topic. In net zero world, the demand for green hydrogen could reach the 660 MMT by 2050. And if you see the India's current hydrogen demand, it is 6 MMT. And most of the hydrogen is used at the refinery, that is 3 MMT, and its fertilizer plant is 2.5 MMT. There is anticipated that the 12 MMT demand by 2030 and almost 30 MMT by 2050. Currently also only 4% hydrogen produced from the water electrolysis process. Therefore, there is a much need to work on it. As you know, the hydrogen production is endothermic reaction, and it absorbs the energy and store in the chemical form of hydrogen. Hydrogen is not a new topic because it is already invented in 1800. The first fuel cell also invented in 1850. The first hydrogen engine also invented in 1900. But after 1950, there is a much research is going on hydrogen for the increase the hydrogen efficiency. If you see the formula, to produce the 1 kg of hydrogen, 50 kilowatt hours of electricity is required. The overall fuel cell and electrolysis system efficiency is only 67%. If you try to produce the hydrogen from renewable, then only 10% is the efficiency of green hydrogen. As you know, the hydrogen can be produced from the electrolysis of water, and DC supply is used for the splitting of this water. If you see the fundamental of it, the enthalpy of water is 285. If you remove the thermal energy, then also we have to give the 237.1 kilojoule of energy to split this water. This is the minimum energy required. And this all electrolysis process depend on the Faraday's first and second law. I will not go deep into it. As already discussed, there are basically 3 types of electrolyzer available in market, and maybe HPCL is also working on the anion-based electrolyzer. But these are the main electrolyzer: alkaline, water electrolysis, PEM, and solid oxide. If you compare the electrolyzer, the alkaline electrolyzer is widely accepted over the global because the operating hours is very high. Also, capex cost is very low. Problem is with the alkaline electrolyzer is only efficiency. If you crack the efficiency, then it is the best electrolyzer. If you see the thermodynamics, only 1.23 volt is required to split the water, but that is the ideal condition. Practically, we have to give almost 2 volt per cell because there is a lot of internal resistance and voltage drop across the electrolyzer. We are doing the research on it, and these are the main formula we are using for the different condition. That is Faraday's law, this hydrogen production rate, and second is the specific energy consumption. The factor influencing hydrogen electrolyzer efficiency is, there is a lot of factors are there, like design, operating temperature, operating pressure, catalyst, which type of catalyst is there, water quality, current density, system integration, like that. Therefore, there is several methods to increase the electrolyzer efficiency. That is increase the operating temperature. In solid oxide, we are operating at almost 700 degrees Celsius. Optimize electrolyte composition like alkaline water electrolysis. Use of advanced catalysts, but catalysts having the problem that is they are having the higher cost. In alkaline electrolysis, we are using the potassium hydroxide and sodium hydroxide, but there is also limit. We can increase the concentration. For potassium hydroxide, we cannot go beyond 30%, and sodium hydroxide, we cannot go above 20%. Also, there is one more problem in the alkaline electrolyzer, that is the formation of bubbles across the electrode. And these bubbles increase the resistance in the electrolyte, which reduces the overall efficiency. Also, this bubble block the active site and reducing the reaction rate. Also, it hinders the ion exchange in the electrolyte, which is cause the inconsistency in hydrogen production and higher power consumption. We are trying to increase the efficiency through the magnetic field, and there is a success. The magnetic field is reduce the cell voltage and also promote the bubble movement, and also this decrease the size of bubble also. Therefore, there is a slight increase in the efficiency. As you know, the nickel is used in electrolyzer, and nickel is the ferromagnetic material. If you apply the external magnetic field, the internal magnetic field also generated in electrolyzer. And this imparted the foreign force, and this foreign force is orthogonal to our electrical field. That's why the particle move perpendicular to magnetic field, and it dissipate our bubbles. There are two types of forces are there, downward force and upward force. You can see in this diagram, without magnetic field, because of hydrogen buoyancy, the most of the hydrogen accumulate on the upper portion of the electrode. And if you give the downward magnetic field, then it goes towards the downward, but it will not solve our problem. Therefore, we try to give the upward magnetic field, and this added to the hydrogen buoyancy, and easily the bubbles can escape from the electrode. These are some results of without magnetic field and with magnetic field. This is a graphical form. If you see that 10% electrolyte concentration, the with magnetic field hydrogen generation is increased. It has almost increased 20 to 30 times. But if you see at the 30% concentration of KOH, then it is a very minor increase in the hydrogen production. Therefore, if you conclude that the magnetic field definitely increases the hydrogen production, but still is in the research phase. And if you apply the at the 10% concentration level, there is a drastic increase in the hydrogen production. But this is not applicable for the 30% concentration level. Also, we see the almost 10% energy reduction in this process. Thank you.
Thanks, Herschel. Thanks for giving enhancing thoughts on how magnetic field can help in enhancing the efficiency of the electrolyzer. So now we conclude our first session. We have tried to cover all the aspects of the hydrogen value chain. which resonates with the theme production, development, and end use of hydrogen. There's a very famous saying which speaks about knowledge is power, and knowledge share is power multiplied. I'm very thankful to all the speakers who have come over here, shared their knowledge with all of us, and I strongly believe that this knowledge will multifold in our own respective fields and will in turn help us achieving Viksit Bharat, energy sufficient Bharat. Thank you all for your time and patient hearing. Thank you all.